Have you ever wondered what makes neural networks so powerful? It's the hidden layers, the magic that happens behind the scenes. In this video, we'll explore how hidden layers work, their purpose, and why they are critical in transforming inputs into smart outputs. So, what exactly are hidden layers? In a neural network, you have three main components: the input layer, hidden layers, and the output layer. While the input layer receives raw data and the output layer produces results, the hidden layers are where the real magic happens. Think of hidden layers as chefs in a kitchen. They take raw ingredients, your data, and process it using learned recipes, the weights and biases. These recipes, fine-tuned during training, transform your input data into something much more meaningful. When data flows into the hidden layer, each neuron, or node, processes the information. Each neuron applies a weight to its input, sums everything up, and passes the result through an activation function to decide whether to activate. This process allows hidden layers to detect patterns in data. For instance, in image recognition, one hidden layer might detect edges, while the next detects shapes like eyes or noses. Each hidden layer in a deep neural network allows the model to learn increasingly abstract features. For example, the first layer might learn to recognize edges, the next layer builds shapes, and the final hidden layers may identify entire objects, like a car, a tree, or even a cat. The neurons in hidden layers apply activation functions to add non-linearity to the model. Without this, the neural network would just be a series of linear combinations, limiting its ability to capture complex patterns. These functions, like ReLU, Tant, or Sigmoid, introduce decision-making capability into the network, allowing it to understand intricate non-linear relationships in data. The Tant function outputs values between -1 and 1, aiding in normalization. Sigmoid takes any input and transforms it into a value between 0 and 1, which is useful for making decisions, especially in binary classification tasks. Here's where things get even more interesting. Hidden layers learn by adjusting their weights during training, using a method called backpropagation. After the network produces an output, it compares it to the expected result and calculates the error. Backpropagation adjusts the weights in the hidden layers to minimize this error, helping the network learn and improve with each cycle. Now, let's look at some real-world examples. Hidden layers are used in everything from self-driving cars to voice assistants and medical diagnostics. They help in processing massive amounts of data to make intelligent decisions in real time. Whether it's identifying obstacles for a self-driving car or detecting early signs of disease in a medical scan, hidden layers power the network's ability to recognize patterns and make smart predictions.